Hello everyone. Today we will first of all study the fundamental counting principle. Fundamental counting principle says if there are n ways to do one task, if there are n ways to do one task, and n ways to do a different task, to do a second task, then together there are n times n ways to do both tasks. If there are n ways to do one task and n ways to do a second task, then together there are n times n ways to do both tasks. Let's look at a simple example first. A man has 6 shirts, 8 pants, and 4 pairs of shoes. In how many ways can he pick a shirt and a pant? By counting principle, we know he has 6 ways to pick a shirt, and he has 8 ways to pick a pant. Together, by counting principle, he has 6 times 8 ways to pick both. That's 48. That means he has 48 ways to pick a shirt and a pant. By counting principle, he has 6 times 8 ways to pick a shirt and a pant. 6 times 8 is 48. Part B. If he needs to wear one of each to work, how many different outfits does he have? If he needs to wear one of each to work, how many different outfits does he have? He needs to wear one of each, means he needs to wear one shirt, one pant, and one pair of shoes. How many different outfits does he have? He has 6 ways to choose a shirt, 8 ways to choose a pant, and 4 ways to choose a pair of shoes. By counting principle, he has 6 times 8 times 4 ways to choose an outfit, which is 6 times 8 times 4, that's 192. So he has 192 different outfits. For every outfit, he must pick a shirt, a pen, and a pair of shoes. He has 6 ways to pick a shirt, 8 ways to pick a pen, 4 ways to pick a pair of shoes. Together, he has this many ways to pick an outfit, and that's why he has 192 different outfits. Part C. Suppose 4 of the shirts, 5 of the pants, 5 of the pants, and 2 pairs of the shoes are green. how many all green outfit does he have? How many all green outfits does he have? All green outfit means he only choose green shirt, green pants, and green shoes. For outfit, he must pick a shirt, a pen, and a pair of shoes. So by counting principle, he has 4 ways. He has 4 ways to pick a green shirt. He has 5 ways to pick a green pen. And he has 2 ways to pick a pair of green shoes. He has 2 ways to pick a pair of green shoes. Together by counting principle, he has 4 times 2 times 5 ways to pick a green outfit. 4 times 5 times 2 is 40. So he has 40 ways. He has 40 ways to have a green outfit. That means there are 40 green outfits. Part D. If he chooses an outfit randomly, what's the probability? What's the probability that he has an all green outfit? If we choose an outfit randomly, what's the probability that he has an all green outfit? Now for probability, keep the formula in mind. Probability is always the number of favorable outcome divided by the number of all possible outcomes. That's the formula for probability, keep it in mind. It's always the number of favorable outcome divided by the number of all possible outcomes. What's the number of all possible outcomes? If we choose an outfit randomly, he has 192 possible outcomes. That's the number of all possible outcomes. If we choose an outfit randomly, he has 192 possible outcomes. That's all possible outcomes. What's the number of favorable outcomes? What we try to find is in how many ways he can have an all green outfit. And we know that he has 40 all green outfit. That's the number of favorable outcomes. So what he wants is an all green outfit. There are 40 such outfits. And the number of all possible outfits is 192. When he chooses the outfit randomly, the number of all possible outfits is 192. So probability is always the number of favorable outcomes divided by the number of all possible outcomes. Then we can reduce. We have divide top and bottom by A. We have 5 over 24. That's the chance that he will have an all green outfit. Next example. A passcode is made randomly using 7 English letters. Part A. What's the probability that no letters repeat? Keep in mind, probability is always number of favorable outcome divided by number of all possible outcome. Let's find the denominator first. In how many ways can we make passcode? Here, a passcode is made randomly using 7 English letters. In how many ways can we make passcode? So passcode is made by 7 letters. 1, 2, 3, 4, 5, 6, 7. In how many ways can we make the passcode? For the first letter, it could be A, B, C up to X, Y, Z. So there are 26 choices. There are 26 letters in total. First letter, there are 26 choices. Also, for the second letter, there are 26 choices. That means we have 26 ways to choose the first letter, second letter, and 26 ways to choose the third letter, the fourth, the fifth, the sixth, the seventh. We have 26 ways to choose each letters. Then by counting principle, together we have 26, 26, 26 times 26. This many ways to make passcode. By counting principle, 26 times 26, 7 times is 26 to the power of 7. That's the denominator. Numerator is the number of favorable outcome. There are 7 letters. 1, 2, 3, 4, 5, 6, 7. What we want is no letter repeats. In how many ways can we make passcode such that no letter repeats? In how many ways can we make passcode such that no letter repeats? No letters repeat. So if we want no letters repeat, from the first letter, we have 26 choice. It could be A, B, C up to S, Y, Z. There are 26 choice. For the second letter, it cannot be the same as the previous one. For the second letter, it cannot be the same as the previous one. So there are 25 choice. It cannot be the same as the previous one. For the next letter, it cannot be the same as the first one, the second one. So there are 24 choice. Then next one, 23 choice, 22, 21, 20. Then by counting principle, multiply them out. By counting principle, multiply them out. 26 times 25, 24, 23, 22, 21, 20. That's a huge number. Let's try to write it using factorial. It can be written as 26 factorial over 19 factorial. This can be written as 26 factorial over 19 factorial. 26 factorial means 26, 25, 24 up to 3 to 1. When I divide by 19 factorial, everything up to 19 will be cancelled. What's left is 26 times 25 times 24, 23, 22, 21, 20. So that's a simple expression for this numerator. Next, we can use calculator to get an answer. Part B. What is the probability that the first 2 letters are vowels? What's the probability that the first 2 letters are vowel? A, E, I, O, U, they are called vowels. Letters A, E, I, O, U, they are called vowels. We have 5 vowels here. What's the probability that the first 2 letters are vowels? So keep in mind, probability is always number of favorable outcome over number of all possible outcome. For the denominator, if we're looking for number of all possible outcome, a passcode is made randomly using 7 English letters. So we have 26 choice for the first letter, 26 choice for the second letter, 26 choice for every letter, and there are 7 letters. So the denominator is 26 to the power 7. That's number of all possible outcome. The numerator is the number of favorable outcome. What we want is that the first 2 letters are vowels. The first 2 letters are vowels. For the first 2 letters, it must be vowels. The rest could be anything. The first 2 letters must be vowels. The other 5 letters could be anything. Let's make choice. First letter could be A, E, I, O, U, one of them, so there are 5 choice. Second letter must also be a vowel, so it could be A, E, I, O, U. Also, there are 5 choice. For the rest, it could be any letters. So there are 26 ways to choose the third letter, 26 ways to choose the fourth one, the fifth one, the sixth, the seventh. So together is 5 squared times 26 to the power 5. If we simplify, we get 5 squared over 26 squared. Then we can use calculator to get an answer. Part C. What's the probability that What's the probability that no letters repeat? And the last three letters are vowels. What's the probability that no letter repeat and the last three letters are vowels? Keep in mind that probability is always number of favorable outcome divided by number of all possible outcome. Keep in mind. That's a formula for probability. Number of favorable outcome divided by number of all possible outcome. Number of all possible outcome. A passcode is made randomly using 7 English letters. So first letter has 26 choice. Second letter has 26 choice. Third one 26 choice. Every letter has 26 choice. So the denominator is 26 to the power 7. Now the numerator, be very careful here, the numerator. No letters repeat. What we want is no letters repeat. And last three letters are vowels. 1, 2, 3, 4, 5, 6, 7. Last three letters must be vowels. Last three letters must be vowels. And the first four letters could be anything. So let's make choice for vowels first. For the first vowel here, it could be either A, E, I, O, U. So there are 5 choices. For the second vowel, we don't have 5 choices now because we use one of the vowels. And no letter repeat. No letters repeat. There's only 4 choices for the vowels. Since we use one vowel already, it cannot be the same vowel again. Last vowel, since we use 2 vowels already, we have 3 vowels left. So we have 3 choices for the vowels here. For the rest, it could be anything. Now, we know that there are totally 26 letters. We use 3 vowels already. There are totally 26 letters. We use 3 vowels already. So there are 23 letters left. There are 26 letters. We use 3 vowels already. So there are 23 letters left. So for the first letter, we have 23 choice. Second letter cannot be the same thing. So 22 choice. Next, 21 choice. 20 choice. So the numerator can be written as first part 23 factorial over 19 factorial. Second part here 5 factorial over 2 factorial. That's 23 factorial over 19 factorial. Everything after 19 will be cancelled. We get 23, 22, 21, 20. For the second part, I can use 5 factorial divided by 2 factorial. I get 5 times 4 times 3. Everything after 3 will be cancelled. Then we can use calculator to get an answer. Next example, a passcode is made randomly, and it must be at least 6 digits, but no more than 8 digits. Part A, what's the probability that the first 3 digits are even? Keep in mind, probability is always number of favorable outcome divided by number of all possible outcomes. Let's find the number of all possible outcomes first. Let's find the number of all possible outcomes first. A passcode is made randomly, and it must be at least 6 digits, but no more than 8 digits. That means it could be either 6 digits, 7 digits, or 8 digits. So there are 3 cases. It could be either 6 digits, it could be either 6 digits, 7 digits, or 8 digits. There are 3 cases. It could be either 6 digits, 7 digits, or 8 digits. In how many ways can we get a 6-digit? In how many ways can we get a 6-digit passcode? 1, 2, 3, 4, 5, 6. We know there are 10 different digits from 0 to 9, 0, 1, 2, 3, up to 9. There are 10 different digits. So for the first digit, there are 10 choices. For the second digit, there are 10 choices. For the third digit, there are 10 choices. So every digit, there are 10 choices. by counting principle multiply together, that's 10 to the power 6. Now, in how many we can get a 7-digit? How many can we get a 7-digit passcode? 1, 2, 3, 4, 5, 6, 7. There are 7 digits. For each digit, there are 10 choices. Together, if by counting principle multiply together, we have 10 to the power of 7. Then, for the third case, in how many we can obtain an 8-digit passcode? 1, 2, 3, 4, 5, 6, 7, 8. For each digit, there are 10 choices. For each digit, there are 10 choices. Together, it's 10 to the power 8. So that's the number of all possible outcomes. That's the number of all possible outcomes. What's the probability that the first 3 digits are even? So again, for a passcode, there are 3 cases. It could be either 6 digit, where the first 3 digits are even, or it could be 7 digit, where the first 3 digits are even, or it could be 8 digits, and the first 3 digits are even. Again, we have three cases. If there are 6 digits, 1, 2, 3, 4, 5, 6, first 3 digits are even. Or it could be 7 digits, 1, 2, 3, 4, 5, 6, 7. First 3 digits are even. Or it could be 8 digits. The first 3 digits are even. How many even digits are there? How many even digits are there? We know that 0, 2, 4, 6, 8 are even digits. So for even digits, we have 5 choices for each. For each even digit, we have 5 choices. Then for the other digits, we have 10 choices. It could be any number from 0 to 9. There are 10 choices. For even digits, there are 5 choices. For other digits, there are 10 choices. For other digits, there are 10 choices. Then together we have, let me write it here. For the denominator, the number of all possible outcomes, it's 10 to the power 6 plus 10 to the power 7 plus 10 to the power 8. For the numerator, in the first case, if there are 6 digits, we have 5 to the power 3 times 10 to the power 3. Second case, we have 5 to the power 3 times 10 to the power of 4. Last case, we have 5 to the power of 3 times 10 to the power of 5. Then we can use calculator to get an answer. Part B. What's the probability that the passcode has 7 digits? And no digits repeat. And no digits repeat. What's the probability that the passcode has 7 digits and no digit repeat? Keep in mind that probability is always number of favorable outcome divided by number of all possible outcome. The number of all possible outcome is a passcode that must be at least 6 digit but no more than 8 digit. The same as the previous part. So the denominator is 10 to the power 6 plus 10 to the power 7 plus 10 to the power of 8. We have this many ways to obtain a passcode that must be at least 6 digits but no more than 8 digits. That's the denominator. That's the number of all possible outcomes. Now for the number of favorable outcomes, we want to have a passcode that has 7 digits and no digit repeat. 7 digits, no digit repeat. 1, 2, 3, 4, 5, 6, 7. 7 digits such that no digit repeat. Seven digits such that no digit repeat. For the first digit, there are 10 choices. It could be any number from 0 to 9. There are 10 choices. For the second digit, since it cannot repeat, so it cannot be 10 choices. It must be 9 choices. We use one number already. We use one digit already. There are 9 digits left. Next digit, it cannot be the same as the first two. So there are 8 choices. Next digit, it cannot be the same as the first 3. There are 7 choices. Next, 6 choice, 5 choice, 4 choice. Together, the numerator is 10 factorial over 3 factorial. Denominator is 10 to the power 6 plus 10 to the power 7 plus 10 to the power of 8. Then we can use calculator to get an answer. Next, let me introduce permutation. A permutation is an arrangement of objects. Where the order of an object matters. Order matters means if I switch order for two objects, it makes difference. For example, AB is not the same as BA. Order matters means if I switch order for two objects, it makes difference. Order matters means if I switch order for two objects, it makes difference. That means order matters. AB is not the same as BA. If I switch order, it makes difference. If I switch order, it makes difference. Next, let's look at a simple example first. List all possible permutations of letters A, B, and C. List all possible permutations for letters A, B, and C. We can try. A, B, C could be a possible permutation. ACB is a different one, since order matters. ACB is a different one. BAC is another one. BCA, CAB, CBA. Here I found 6 different permutations. Do we have them all? Is there a way to check how many permutations are there? Let's think of the problem this way. We know that for every permutation, we try to arrange 3 letters. For every permutation, we try to arrange 3 letters. For the first letter, I can pick either A, B, or C, so there are 3 choices. For the second letter, since I used one already, there are 2 letters left. I have 2 choices. For the last letter, there's only 1 choice, since I used 2 letters already. Then together, by counting principle, since there are 3 ways to choose the first letter, 2 ways to choose the second letter, 1 way to choose the last letter. So there are 6 possible permutations. There are 6 possible permutations for 3 letters. Think of different one. If we have 10 letters, A, B, C up to J, how many different permutations are there? How many different permutations are there? Let's try the same way. Try the problem the same way. We have 10 letters. For every arrangement, for every permutation, we arrange 10 letters in a row. For every permutation, we arrange 10 letters in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For every permutation, we arrange 10 letters in a row. In how many ways can we choose the first letter? I can use any one of these 10 letters, so there are 10 choices. In how many ways can we choose the second letter? Since I used one already, there's only 9 letters left, so there are 9 choices. Then 8 choice, 7 choice, 6, 5, 4, 3, 2, 1. This number, by counting principle, we multiply them out. If we multiply all these 10 numbers together, it's 10 factorial. In the previous problem, number 6 can be written as 3 factorial. Based on those two examples, let me introduce the first permutation rule. Permutation rule number 1. The number of ways to arrange n distinct objects in a row is n factorial. That's permutation rule number 1. The number of ways to arrange n distinct objects in a row is n factorials. For example, in the first example here, the number of ways to arrange 3 letters is 3 factorial. The number of ways to arrange 10 letters is 10 factorial. So in general, the number of ways to arrange n objects is n factorial. Next, let's look at an example. Consider a group of 20 students. Consider a group of 20 students. First question. In how many ways can we arrange all 20 students in a row? In how many ways can we arrange all 20 students in a row? So by permutation rule number 1, the number of ways to arrange n objects is n factorial. So the number of ways to arrange 20 students is 20 factorial. The number of ways to arrange 20 students is 20 factorial. Part B. In how many ways can we arrange six of the students in a row? In how many ways can we arrange 6 of the students in a row? 1, 2, 3, 4, 5, 6. We try to arrange 6 students in a row. For the first person, there are 20 choices. It could be any one of these 20 people. So once we make choice for the first person, there are 19 students left. So for the second student, there are 19 choices. Once we make choice for 2 students, there are 18 students left. Next one have 18 choice, 17 choice, 16 choice, 15 choice. By counting principle, we multiply them out. There are 20 choices for the first student, 19 choices for the second student. By counting principle, multiply them out. That can be written as 20 factorial over 14 factorial. 20 factorial over 14 factorial. Part C. In how many ways can we arrange 12 students in a row? 12 of the students in a row. In how many ways can we arrange 12 of the students in a row? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We try to arrange 12 students in a row. So for the first student, there are 20 choices. Next one, 19 choices. Next one, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9. Then, by counting principle, multiply them out. Then write it as a factorial. I can write it as 20 factorial over a factorial. I can write it as 20 factorial over a factorial. Next, based on the previous example, let me introduce permutation rule number 2. Suppose there are n distinct objects. Suppose there are n distinct objects. The number of ways to arrange k of an object is n factorial over m minus k factorial. Denoted by P and K. So in general, we write P and K equal to n factorial over m minus k factorial. In general, we write P and K equal to n factorial over m minus k factorial. That's permutation rule number 2. If we look at the previous example here, we can see that the number of ways to arrange 6 students out of 20 is the total 20 factorial over 20 minus 6, that's 14 factorial. The number of ways to arrange 12 students out of 20 is the total 20 factorial over 20 minus 12, which is a factorial. That's permutation rule number 2. Now let's look at an example here. Consider a group of 15 people where Peter is the group leader. Part A. When we arrange all 15 people in a row, what's the probability that Peter is in the center of the row? Keep in mind that probability is always the number of favorable outcomes divided by the number of all possible outcomes. Let's find the denominator first. What's the number of all possible outcomes? In how many ways can we arrange all 15 people in a row? By permutation rule number 1, we know that we have 15 factorial ways to arrange all 15 people in a row. That's the denominator. All possible outcomes. Next, let's find out the number of favorable outcomes. What we want is Peter in the center of the row. In how many ways can we arrange 15 people where Peter is in the center? So let's draw a picture first. 15 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 people. If we try to guarantee Peter in the center, we must first of all put Peter in the center. 1, 2, 3, 4, 5, 6, 7, 8. Put Peter here. I need to first of all put Peter in the center. We know that there are 15 people. If I put Peter in the center, there are 14 people left. If I put Peter in the center, there are 14 people left. And the number of ways to arrange 14 people is 14 factorial by permutation rule number 1. The number of ways to arrange 14 people in a row is 14 factorial by permutation rule number 1. If we simplify here, I get 1 over 15. Part B. When we arrange 10 people in a row, when we arrange 10 of the people in a row, what's the probability that Peter is in a row? When we arrange 10 people in a row, what's the probability that Peter is in a row? So keep in mind that probability is always number of favorable outcome divided by number of all possible outcome. Let's find the number of all possible outcome first. We try to arrange 10 people out of 15 in a row. By permutation rule number 2, that's P15, 10. Permutation 15 choose 10. That's permutation 15 choose 10. That's the number of all possible outcome. Next, let's try to find the number of favorable outcome. Number of favorable outcome. We want to arrange 10 people where Peter is in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We try to arrange 10 people where Peter is somewhere in a row. In order to guarantee Peter in a row, we need to put Peter in a row first. In order to guarantee Peter is in a row, we must put Peter in a row first. So when I put Peter in a row, Peter has 10 choices. He could be here, 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 here. He could be anywhere. He has 10 choices. When we try to put Peter in a row, we have 10 choices. There are 10 ways to put Peter in a row. So Peter somewhere, put it somewhere in a row. There are 10 ways to put Peter in a row. Once I put Peter in a row, there are 14 people left. There are totally 15 people. Once I put Peter in a row, there are 14 people left. And we have 9 more positions here. We have 9 more positions. There are totally 10 places. Once I put Peter in a row, there are 9 more places left here. There are 9 more places. So the number of ways to arrange 9 people out of 14 is permutation 14 choose 9. The number of ways to arrange 9 people out of 14 is permutation 14 choose 9. That's permutation rule number 2. Then simplify this expression. 14 choose 9. Permutation 14 choose 9 is 14 factorial over 14 minus 9 is 5 factorial. Permutation 15 choose 10 is 15 factorial over 15 minus 10 is 5 factorial. If we simplify here, I have 10 times 14 factorial over 5 factorial times the reciprocal 5 factorial over 15 factorial. 5 factorial get cancelled. 14 factorial over 15 factorial. If I simplify, I get 1 over 15 times 10. That's 10 over 15. That's 2/3. When you are doing probability, be very, very careful. Probability is always a number between 0 and 1. If we get a number more than 1, or we get a number less than 0, the answer must be wrong. Probability is always a number between 0 and 1. 1 over 15 and 2 over 3. A probability is always a number between 0 and 1. Next, part C. When we arrange 7 people in a row, when we arrange 7 of the people in a row, what's the probability that Peter is not in a row? When we arrange 7 people in a row, what's the probability that Peter is not in a row? So keep it in mind, probability is always number of favorable outcome divided by number of all possible outcome. For the denominator, number of all possible outcome. In how many ways can we arrange 7 people? In how many ways can we arrange 7 people in a row out of 15 people? By permutation rule number 2, that's P 15 7. That's the number of ways to arrange 7 people out of 15 in a row. That's the number of all possible outcome. For the numerator, the number of favorable outcome. All we want is Peter not in a row. We try to arrange 7 people. 1, 2, 3, 4, 5, 6, 7. What's the probability that Peter is not in a row? That means we don't want Peter in a row. If Peter is not in a row, that means we cannot choose Peter here. We cannot choose Peter out of 15. So Peter is out. We have 14 people left. We try to arrange 7 people out of 14 other people in a row. It's permutation P14 choose 7. The number of ways to arrange 7 people out of 14 is permutation 14 choose 7. Then simplify. The numerator is 14 factorial 14 minus 7. 14 minus 7 is 7 factorial. Denominator permutation 15 choose 7. That's 15 factorial over 15 minus 7 is 8 factorial. If we simplify, we have 14 factorial over 7 factorial times 8 factorial over 15 factorial. Fifth, 14 factorial over 15 factorial is 1 over 15. And 8 factorial divided by 7 factorial is 8. So you get A over 15. Next example. When all 7 letters A, B, C, D, E, F, G are arranged together to make string, find each of the following probabilities. Part A. What's the probability that the string contains a substring of A, B? So for probability, we can try to find the denominator first, the number of all possible outcomes. How many possible outcomes are there? In how many ways can we arrange 7 letters together? By permutation rule number 1, the number of ways to arrange 7 letters is 7 factorial. That's the denominator, the number of all possible outcomes. That's the denominator, the number of all possible outcomes. The numerator is the number of favorable outcomes. What we want is we want to have AB together. In order to guarantee a substring of AB, we must group AB together. So group AB together, consider AB is one object. Then we have other objects, C, D, E, F, G. If I group AB together as one object, we have 6 objects here. The number of ways to arrange 6 objects is 6 factorial. If I group AB together as one object, we have 6 objects left. The number of ways to arrange 6 objects is 6 factorial. Then 6 factorial over 7 factorial is 1 over 7 if we simplify. Part B. What's the probability that the string contains a substring of ABC What's the probability that the string contains a substring of ABC? So let's find denominator first, the number of all possible outcomes. We try to arrange 7 letters together to make a string. So the number of all possible outcomes is 7 factorial by permutation rule number 1. The number of ways to arrange 7 objects together is 7 factorial. Then for the numerator, the number of favorable outcomes, what we want is we want a substring of ABC. If we want to guarantee ABC together, we must combine ABC together as one object. We must combine ABC together as one object. Then we have D, E, F, G. That means we have a total of 5 objects. We have a total of 5 objects. The number of ways to arrange 5 objects is 5 factorial. The number of ways to arrange 5 objects is 5 factorial. Then we simplify. 5 factorial over 7 factorial is 1 over 42. Part C. What is the probability that the string contains substrings A, B, and C, D? What's the probability that the string contains substrings A, B, and C, D? So we can find denominator first. The number of all possible outcomes is 7 factorial. The number of all possible outcomes is 7 factorial. For the numerator, we try to find out the number of favorable outcomes. For a number of favorable outcomes, when we have AB, substring AB, and substring CD, so we must put AB together as one object. Put CD together as one object. What's left is E, F, G. So we have a total of 5 objects. The number of ways to arrange 5 objects is 5 factorial. If we simplify, that's 1 over 42. Next, part D. What's the probability that the string contains a substring of AB, but doesn't contain a substring of CD? How can we approach this problem? Let's think of events. Let event X represent the string contains a substring of AB. Let me use X and Y here. Let event X represent that the string contains a substring of AB. Let event Y represent the string contains a substring of CD. Let event X represent the string contains a substring of AB. Let event Y represent the string contains a substring of CD. Then what we are looking for is what's the probability that the string contains a substring of AB but doesn't contain a substring of CD? So in this problem, what we are looking for is probability of X intersection Y complement. X intersection Y complement. The string contains substring of AB, but doesn't contain a substring of CD. X intersection Y complement. Then how can we write this? We can use Venn diagram. Assume that's event X, that's event Y. X intersection Y complement. That means X occurs, but Y doesn't. It contains substring of AB, but not CD. X occurs, but Y doesn't. So this set here, if I use probability, I can write it as probability of X, the entire circle, minus the intersection, probability of X intersection Y. So X intersection Y complement can be written as probability of X minus probability of X intersection Y. Then what's probability of X? Probability of X represents what's the probability that the string contains a substring of AB. That's what we found in part A. What's the probability that the string contains a substring of AB? That's 1 over 7. So probability of X is what we found in part A. That's 1 over 7. What's probability of X intersection Y? What's probability of X intersection Y? That means both X and Y, both event occurs. X intersection Y means both event X and Y, they both occurs. That means the string contains a substring of AB and CD. What's the probability that the string contains substrings AB and CD? That's what we found in part C. What's the probability that the string contains both substrings AB and CD? That's X intersection Y. The string contains substrings AB and CD. Intersection means N. So we have 1 over 42. Probability that the string contains substrings AB and CD is 1 over 42. Then subtract. We get 6 over 42 minus 1 over 42. That's 5 over 42. Next, let's look at a different example here. List all possible permutations for letters A, B, B, and find the number of permutations. Here, in this example, A, B, B, these two letters B and B looks exactly the same. In order to use the old technique, we try to make this B looks different. So let's call them A, B1, and B2. Now let's make arrangement for these three letters. We know that for three different letters, the number of ways to arrange three objects is 3 factorial, which is 6. We know that if they are different letters, we have 6 different arrangements. Let's write them out first. We have A, B1, B2. That's one arrangement. I have A, B2, B1. That's another one. I have B1, A, B2, or B2, A, and B1, or B1, B2, A, B2, B1, A. So here we see that the number of ways to arrange 3 objects is 6. 3 factorial equal to 6. But the thing is here, since B1, B2, they are exactly the same letter, they are both letter B's. So these two outcomes, these two arrangements, they are exactly the same. They both represent A, B, B. These two arrangements, they are exactly the same. They both represent B, A, B. And these two arrangements, they are exactly the same. They both represent B, B, A. So here we see that we have 3 permutations. So the answer is 3 permutations here. We have 3 different permutations. Another example. lists all possible permutations of letters A, B, B, B. And find the number of permutations. So in order to use an old technique here, we try to make this BBB different because these 3B, they are exactly the same. In order to use an old technique, we try to make these 3B different. Let's assume the letters are A, B1, B2, B3. In order to use an old technique, we try to make these 3B different. So call them B1, B2, B3. Then by the old technique, we know that the number of ways to arrange 4 letters in a row is 4 factorial, which is 24. So we know that if these B's are different, we have 24 different arrangements. If these B's are different, we have 24 different arrangements. So we have A, B1, B2, B3. That's one of them. A, B1, B2, A, B1, B3, B2. That's a different one. A, B2, B1, B3, A, B2, B3, B1, A, B3, B1, B2, A, B3, B2, B1. We have 24, so let's write them all. B1, A, B2, B3. If we write that correctly, it should be 24 different permutations. B1A, B3, B2, B2A, B1, B3, B2A, B3, B1, B3A, B1, B2, B3A, B2, B1. Continue. If we write that correctly, we should get 24 different permutations. B1, B2A, B3, B1, B3, A, B2, B2, B1, A, B3, B2, B3A, B1, B3, B1A, B2, B3, B2A, B1. Continue, we may have B1, B2, B3A, B1, B3, B2A, B2, B1, B3A, B2, B3, B1A, B1, B2, B3A, B1, B3, sorry, I messed up. It should be B3, B1, B2A, B3, B2, B1A. Here we got 24 different permutations. But the thing is, B1, B2, B3, they are exactly the same. They all represent B's. So everything in the first column, they all represent A, B, B, B. And everything in the second column, they all represent B, A, B, B. Everything in the third column, they all represent B, B, A, B. everything in the last column, they all represent B, 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 A. So here we only have 4 different permutations. So here we only have 4 different permutations. There are 4 different permutations. So here we only have 4 different permutations. Next example. List all possible permutations of letters A, A, B, B, and find a number of permutations. Here we see that letter A's, this 2A looks exactly the same, and this 2B's looks exactly the same. In order to use an old technique, we need to make the A's looks different and make the B's looks different. So make A looks like A1, A2, make B's to be B1, B2. Then they all looks different. Now they are all distinct objects. Then we can apply permutation rule number 1. The number of ways to arrange 4 distinct objects is 4 factorial. The number of ways to arrange 4 different letters is 4 factorial, which is 24. So let's write down all possible permutations. If we write that correctly, we should get 24 permutations. So we have A1, A2, B1, B2, A1, A2, B2, B1, A2, A1, B1, B2, A2, A1, B2, B1, A1, B1, A2, B2, A1, B2, A2, B1, A2, B1, A1, B2, A2, B2, A1, B1. Let's continue. If we write that correctly, we should get 24 different permutations. A1, B1, B2, A2, A1, B2, B1, A2, A2, B1, B2, A1, A2, B2, B1, A1. Continue. B1, A1, A2, B2, B2, A1, A2, B1, B1, A2, A1, B2, B2, A2, A1, B1. Continue. We have B1, A1, B2, A2, B2, A1, B1, A2, B1, A2, B2, A1, B2, A2, B1, A1. Then we have B1, B2, A1, A2, B2, B1, A1, A2, B1, B2, A2, A1, B2, B1, A2, A1. So we have 24 different permutations for 4 different letters. If they are different letters, we have 24 different permutations. However, A1, A2, they are exactly the same. B1, B2, they are exactly the same. So everything in the first column represents A, A, B, B. Everything in the first column represents A, A, B, B. Everything in the second column represents A, B, A, B. Everything in the third column represents A, B, B, A. Everything in the fourth column represents B, A, B. Everything in the fifth column represents B, A, B, A. everything in the last column represents BBAA. So here we can see that there's only 6 different permutations. So there are 6 different permutations. Is there any quicker way to find this without writing everything down? Is there a quicker way to find out how many permutations are there? So originally we can see that there are 3 letters. When we make permutation for 3 letters, we have 6 different permutations. But since these 2 bits are the same, if I switch order for these 2 bits, it makes no difference. So we can compute this in a different way. There are totally 3 letters. We first of all make permutation for 3 letters, we get 3 permutations. However, these 2 bits looks exactly the same. When I switch 2 bits, it makes no difference. So I can divide by 2 factorial. Since I switch 2 objects, it makes no difference. There are totally 3 objects. But when I switch 2 of an objects, it makes no difference. I have 3 factorial over 2 factorial, which is 3. Let's match what we have here. There are 3 different permutations. For the next example here, these 3 letter bit looks exactly the same. If I make them different and make arrangement, we have 4 factorial. If I make these bits look different and make arrangement, there are 4 factorial. We have 24 different arrangements. If I make the bits look different. However, these 3 bits looks exactly the same. If I switch order for these 3 bits, it makes no difference. And the number of ways to switch order for 3 objects is 3 factorial. The number of ways to switch order for 3 objects is 3 factorial. So since 3 bits look the same, when I switch order for these 3 bits, it makes no difference. The number of ways to switch order for 3 objects is 3 factorial. So I take the total, 4 different letters, but 3 bits looks exactly the same. So I take 4 factorial divided by 3 factorial, which is 4. We have 4 different permutations. Let's match what we have here. In this example here, we have 4 letters, but 2 A's looks exactly the same. 2 B's looks exactly the same. The number of ways to make arrangement for 4 different objects is 4 factorial. However, since 2 A's looks exactly the same, when I switch order for 2 A's, it makes no difference. 2 B's looks exactly the same. When I switch order for these 2 bits, it makes no difference. So I can take 4 factorial divided by 2 factorial, 2 factorial. The number of ways to switch 2 A's is 2 factorial. The number of ways to switch 2 b's is 2 factorial. So I take, there are totally 4 different letters. There are totally 4 letters. But 2 A's are the same. So I divide by 2 factorial. 2 b's are the same. I divide by 2 factorial. Because the number of ways to switch 2 A's is 2 factorial. The number of ways to switch 2 b's is 2 factorial. And when I switch A's and B's, it makes no difference. That's why I take 4 factorial divided by 2 factorial divided by 2 factorial. 4 factorial is 24. 2 factorial is 2. 2 factorial is 2. 2 times 2 is 4. 24 divided by 4 is 6. So let's match what we have here. So there are 6 different permutations. Now, based on this experiment, let me introduce permutation rule number 3. Permutation rule number 3 says, suppose there are n objects. With n1 objects of type 1. n1 objects of type 1. n2 objects of type 2. And so on. Then the number of ways to arrange all n objects is n factorial over n1 factorial times n2 factorial, and so on. N factorial over n1 factorial, n2 factorial, and so on. That's permutation rule number 3. Next, let's try an example. How many different strings can be made using all letters from the word Mississippi, how many different strings can be made using all letters from the word Mississippi? In the word Mississippi, there are totally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are totally 11 letters. We have letter I 4 times. Letter S 4 times. Letter P twice. We have letter I 4 times. Letter S 4 times, letter P twice. So by permutation rule number 3, the number of ways to arrange 11 letters with I 4 times, S 4 times, P twice is 11 factorial over 4 factorial over 4 factorial times 2 factorial. That's by permutation rule number 3. And we can use calculator to get an answer. Next example. How many different strings can be made? Using all letters from the word success, SUCCESS. How many different strings can be made using all letters from the word success? So here we have a total of 1, 2, 3, 4, 5, 6, 7. We have a total of 7 letters, where we have S 3 times, letter C twice. Those are the repeating digits. Those are the repeating letters. Then take the totally 7 factorial divided by 3 factorial divided by 2 factorial. We can use calculator to get an answer. Next example, when 12 dice are rolled, find each of the following probabilities. Part A, what's the probability of getting 5 fours, 4 sixths, and 3 ones? When 12 dice are rolled, what's the probability of getting 5 fours, 4 sixths, and 3 ones? So we're looking for the probability of getting number 4 5 times, getting 4 5 times, getting 6 4 times, getting number 1 3 times. Probability is always, keep in mind, probability is always number of favorable outcome divided by number of all possible outcome. When we roll 12 dice, what's the number of all possible outcome? Every die has 6 outcome. Every die has 6 outcome. So we have 6 times 6 times 6, 12 times, which is 6 to the power of 12. Every die has 6 outcomes. So 12 die together will be 6 to the power of 12. That's the number of all possible outcomes. That's the denominator. For the numerator, we have 12 different numbers. We have 12 different numbers. 5 of them are the same. 5 of them have one type. 4 of them have a different type. 3 of them have different type. The number of ways to arrange 12 objects is 12 factorial. But 5 of them have one type. So divide by 5 factorial. 4 of them have a different type. Divide by 4 factorial. 3 of them have another type. Divide by 3 factorial. That's permutation rule number 3. So denominator is 6 to the power 12. Numerator is 12 factorial. The number of ways to arrange 12 number is 12 factorial. Then 5 of them have one type. 4 of them have a different type. 3 of them have another type. So 12 factorial divided by 5 factorial, 4 factorial, 3 factorial. Then use calculator, we can get an answer. Part B. What's the probability of getting each number exactly twice? What's the probability of getting each number twice? What's the probability of getting each number twice? For probability, always use the formula number of favorable outcome divided by number of all possible outcome. Number of all possible outcome here is 6 to the power 12. When we roll 12 dice, every die has 6 outcomes. So 6 times 6 times 6, 12 times is 6 to the power of 12. That's the denominator. Numerator, what's the probability of getting each number twice? That means we get number 1 twice. We get number 2 twice. We get number 3 twice. We get number 4 twice. We get number 5 twice. We get number 6 twice. So there are totally 12 numbers. We try to make arrangement for 12 numbers, where we have number 1 twice, 2 twice, 3 twice, 4 twice, 5 twice, 6 twice. So I divide 2 factorial for this number, for these 2 ones. 2 factorial for these 2 twos. 2 factorial 6 times. 2 factorial for each 6, for each number here. So that's the final answer. We can use calculator to find the answer.